それでは時間となりましたので、セミナーを開始いたします。本日、座長を務めますのは、九州大学アジアオセアニア研究教育機構コーディネーターのキム・シューマハ准教授です。シューマハ先生、よろしくお願いいたします。
Hello, everyone. Thank you for the kind introduction. And I would like to welcome everyone today to the 142nd edition of the Brown Bag Seminar hosted by QAOS at Kyushu University. And today, it is my great pleasure to welcome Associate Professor Brian Kenji Iwana, who will be talking about advances in temporal pattern recognition and its effect on AI. And a little bit of background around Professor Iwana is he's now a member of the Department of Advanced Information Science at the Graduate School of Information Science and Electrical Engineering at Kyushu University. He was born in Mission Viejo in California, USA. He received his bachelor's in science in computer engineering at the University of California, Irvine. After getting his bachelor's, Professor Iwana worked as a software developer at the NASA in Mountain View, California. Then he returned to academia and received his PhD from the Graduate School of Information Science and Electrical Engineering at Kyushu University. He was also a graduate from the Graduate Education Research Training Program in Decision Science for Sustainable Society, also at Kyushu University. Since then, he worked as a postdoc, assistant professor, and then now in his current position as an associate professor, all at the Graduate School of Information Science and Electrical Engineering. And then furthermore, he's affiliated with like a multitude of different initiatives, such as in teaching, supervision, or like editing of academic journals. His research interests include time series recognition, dynamic program, artificial neural networks, document recognition, and natural language processing. And after his talk, after his presentation, as was already mentioned, there will be a Q&A session where you can post your questions into the chat if they're in Japanese or in English. So either way, please do not hesitate to ask any questions at the end of his presentation. But without further ado, I would like to hand it over to Professor Iwana. And we are very much looking forward to your presentation and looking at your very impressive CV and track record. I'm sure this will be a wonderful presentation. So Professor Iwana, please, we're looking forward to your presentation. You're still on mute, Professor Iwana, just to...
Okay, can you see my screen? Is it
Perfectly.
shared?
Yes, perfect.
Okay, great. Okay, thank you for the introduction. My name is Brian Kenji Iwana, like you mentioned, and I'll talk about advances in temporal pattern recognition and its effect on AI. So since I was already introduced, I'll skip through this slide. So I'm an associate professor in the Human Interface Laboratory. In our lab, we have 2 professors, 2 associate professors, and 2 assistant professors. We actually have about 40 students, and of these 40 students, 7 of them I supervise directly. This is a rough interview of the topics we study in our lab. Actually, we cover a ton of different topics and all the way from applied applications and stuff, all the way down to the fundamental machine learning theory. And actually, so this presentation will be maybe a little bit different than most brown bag seminars, maybe a little bit more technical, because most brown bag seminars all live up here in the applied areas. So like what you can do with research, but most of my research happens down here in the fundamental area. So I'll be talking about a little kind of different stuff than normal. Okay. So to give a little better idea of the main topics we study in our lab is we do document recognition, like which is recognition of various things like books and actually physical documents. And then we also do bioinformatics, like stuff for medical and biology and machine learning theory. And then what I'll be talking about is time series recognition. So before we get started, first I should introduce pattern recognition and give you some of the basics of what it means to do pattern recognition. So it's always easier with an example. So in this example, what pattern recognition might do is it might ask a question like, what is this? So what is this object? Obviously, for a human, it's super easy. It's obviously a car, right? It maybe took longer for it to appear on my screen than you to recognize that is a car, right? But that's because humans have a amazing pattern recognition ability. We are natural pattern recognition machines. But this is a problem for computers because what does a computer see? Actually, a computer could only see data. It only sees numbers like ones and zeros coming in from the camera. So the main task and the main purpose of pattern recognition is to use computers to see these numbers and translate it into what some kind of understanding of the data. So we want to, for example, take these numbers in. Sorry, okay, now the recording came back. Okay, yeah. So that's what we're the aim of pattern recognition is. And to more explain roughly how it works is that basically we can provide a computer with a bunch of data, and then the computer will use machine learning to learn from the data, and then the computer will make a decision about the data. So in this example, I want to know whether this green object is it a fish or a car? So we can give the computer a bunch of different fish and a bunch of different cars or pictures of cars and fish, and then it'll learn from this data, and then it'll be able to make a line in some space on basically on whether things on one side of this line is a fish or one side of this line is a car. And so in this way, we can make a classifier to learn what a car and what fish are. So this is roughly how pattern recognition works with computers. And actually, another really cool example is generative AI. So, for example, like this really recently, we can generate pretty nice pictures from text. So I gave a model called Dolly this text saying Brown Bag Seminar for Kyushu University Institute of Asian Oceanic Studies and a seminar for sharing research. So I gave a model this text and it created these two pictures. I think they're pretty good. They did a pretty good job in representing what Brown Bag Seminar is. Yeah. So this is just, yeah, some brief introduction. So now I will move on to what time series recognition is and what I actually study. Okay. So first I need to explain a little more about what a time series is. So this is an example of a really simple example of a time series. Basically, a time series is a sequence of data points that's measured over time. So each one of these is we would call an element of the time series, and it's basically just some value over these time steps. And technically, sequences and time series are different, but for most cases, they're treated the same in temporal pattern recognition. And actually, time series are everywhere. So while time series recognition is maybe not the most flashy and popular type of data, we actually use it without realizing it. So like, for example, some very common thing is like for audio, right? So audio is a bunch of data that happens over time, right? As the, like, for example, speech or stock, right? So stock is another example of some data over time. And handwriting. So like maybe some people might have or like on your phone when you want to write a character in some pad, you have some order to the handwriting, right? So when you draw this 2, I start from here and I draw, I mean, it goes like this, right? So it has order. And also stuff like sequences like DNA also uses temporal pattern recognition. And there's also many more things like actions and bio forensics and stuff like that. Anyway, the key challenge and the key difference between time series and other types of data is that order matters. So this is a really big point. So both of these, for example, both of these 2s, I guess you call it 2s, both of these 2s have the same data points. So the blue dots are in the same spot. But because this one has an order that matters, this is obviously a 2. But in this one, I just picked some random order, and because of the random order, it's not a 2 anymore, right? So you can see how important that the order matters just as much as where the locations of the data is. So this is our biggest challenge and biggest reason why many pattern recognition methods don't work with time series. And then there are also, besides the order, there are many other challenges in time series pattern recognition. For example, we have patterns of different lengths and patterns of different rate. So for example, this pattern and this pattern, they look similar, and so maybe they should be treated similar, but this one is much more dense, right? And then this one is much more sparse. So because of that, maybe some pattern recognition methods might see these as 2 different patterns when they should be the same pattern. And then we also have something called temporal distortions. So in temporal distortions, maybe they're distorted in some way in the time dimension. So there might be a bunch grouped up over here and very few over here. But our main goal of time series recognition and temporal pattern recognition is we want to see all time series that are kind of like this, but we want to see them as one thing, right? And so we can differentiate this versus another time series, if that makes sense. Okay. So now I'm going to cover a little bit more about the history of time series recognition and where it brings us to today. So in very classical methods, there are basically 2 main methods of doing temporal pattern recognition. And the first one is called embedding methods. So the general idea of embedding method is that to use a time series in some kind of vector space, we have to represent the time series as a single point. And in these embedding methods would take somehow, for example, bag of words can take a time series and wrap the whole series up into a single point. And then using this, we can make some classifier to draw a line between the 2 classes, like this. And then the second method is called distance-based methods. So in distance-based methods, instead of representing the whole time series as a point, we can find the distance between points, or the distance between time series, and draw the space using that. So for example, using something called dynamic time ordering, right? We can classify stuff based on how far away the green dot is to the other dots, right? But these are classical methods. And more recently, we have something called artificial neural networks. And in this case, this one is called, this is a multi-layer perceptron. And actually, neural networks are a really old idea. They came out even at the beginning of other methods, but not until recently, neural networks have become really popular and dominated the field. Nowadays, almost all research in pattern recognition is done using neural networks, and we don't use the classic time series methods much anymore. Anyway, so the idea of a neural network is that we have something that looks like this, and the way it works is that there's basically layers. You can see these lines of nodes, and each node is like a neuron, or is a neuron, and it's very similar to how brains work. So in a human brain, we have biological neurons, and each of the neurons, they function by gathering a bunch of inputs, processing the input, and making an output. And then we have millions of these, where is a neural network is very similar. So I color-coded the colors to be similar. So we in a single neuron, in an artificial neural network, we have a bunch of inputs, and then it processes it, and then outputs to the next layer, right? So you can see how it's very similar, right? And actually, multi-layer perceptrons, they can be used well with time series recognition. So the most easiest way is that we can take each time step of the time series and input it into the MLP. So you can see the green becomes green here, the blue here, and the red's here, right? And then it works just like a normal MLP, like a neural network. And it does these small calculations and does some prediction at the end. But there's kind of a problem with using MLPs with time series. And the problem is that we have the thing that I talked about before, temporal distortions. So remember when I said that we have the problem of sometimes data might have some distortion where data was maybe like clumped up like this. Well, in time series recognition, or in a temporal MLP, if we take these two time series and put it in, you can see the colors don't line up. So where this is red in this one is now blue in this one, right? And so you can see how this might cause a problem. So the problem with these MLPs is that they're very rigid and they're not flexible to problems of temporal pattern recognition. So to solve this problem, a whole branch of study was created. So now we have temporal neural networks. And in temporal neural networks, these are networks that specifically challenge the issues of time series. And one of the most famous temporal neural networks is called a recurrent neural network. I won't explain the very details, but the main difference between a recurrent neural network and a normal MLP is that it has this thing called a recurrent connection, right? And this recurrent connection allows us to pass the data in and it lets the state learn about the data, and it's able to overcome many of the temporal distortions and time dependency problems that MLPs have. Anyway, so at the same time of temporal pattern recognition, we have image-based recognition, a whole image domain. And actually, the image domain is thriving even more than the temporal domain. Anyway, yeah. So, but the major achievement of temporal or of image recognition is something called a convolutional neural network. And actually, the convolutional network borrowed ideas from something called a time delay neural network back in the time series. So it has an origin of time series. And the main difference between a convolutional network and other neural networks is it has this convolution, this thing we call, or like this thing of shared weights, and it's called a filter. But anyway, basically, we have these weights that pass over the image to learn features of the image, and it happens in these convolution layers. It's a little more complicated, but it's not the point. So, yeah, but actually, more importantly, CNNs can also be used for time series. So while so we had so many advances in image recognition because of CNNs, a lot of the research from image CNNs came back down to time series CNNs. So, and to use a CNN with a time series, it just requires some very tiny modification of changing something from something called a 2D convolution to a 1D convolution. But this small change was able to have huge advances in time series recognition. And these are just some random examples from one of my papers where temporal convolution networks, we can achieve state-of-the-art results on so many different time series, like handwriting or activities or speech, right? So we can have near perfect accuracy using temporal convolutions. And actually, this is the probably still the main state-of-the-art model that's used very commonly in temporal pattern recognition. And finally, that brings us to transformers. So transformers are a really new model that their origin is essentially their MLP that I talked about before, but with some extra tricks. And the extra tricks are stuff like self-attention, residual connections, and some special encoding. So I'm going to explain this diagram very briefly. So in this diagram, we have a transformer looks something like this. It's normally drawn like this. And each one of these red boxes, these are the inputs. And then these inputs have some kind of embedding, like kind of embedding methods like before. And then the embeddings are entered into the transformer layer. And inside the transformer layer, we have a self-attention layer, and then an MLP. So it says fully connected layer, but fully connected layer and MLP are the same thing. And then it has some output embeddings. And this is just generally the structure of the way transformers look like. But actually, this whole time, I left out one huge important type of temporal data, and that's language. So language is a whole nother field of popular time series and sequences. So for example, the sentence like the cat ate food, it can be entered into a transformer, or actually any of the networks we talked about. Language can be entered into it one step at a time. So in this case, instead of having a data point in a time series, we have each word is one time step, or each part of a word is a time step. And actually, transformers were originally designed for language, but they could be used for other things, all types of data. And actually, most of you have already used transformers before. So in ChatGPT has become really popular, but the T in ChatGPT stands for transformer. So this transformer, this thing for time series, is used in ChatGPT. And actually, it's also used in many other models, like other generative models. Like the image I made before, it also has a transformer. So the text encoder is a transformer. But it also has other networks like CNNs, like I showed before. So you can see how modern methods, they use pieces from all fields, including time series. Okay. So now I will introduce some really brief introductions of my research and what we do in my lab. So I'll start with some easy topics and then go into more complicated ones later. So this is just some fun examples. So in this research, I have a student and he's trying to develop a method of controlling the way we can generate pictures. So he wants to generate pictures, but instead of placing the items with sentences, we're trying to replace the items with like this kind of input grid. So given this input grid, I could place cat, grass, and apple, and it'll generate pictures of a cat and some grass and an apple in the right places. So this is his goal. And my lab also does many other generative research, mostly with focusing on generating fonts. So we generated fonts from other fonts. So given some pieces of fonts, we can generate other fonts, or we generated fonts from patterns, and we also generated fonts just from the book cover. So plain book cover, no text, and we could generate fonts. And I also have collaborations using natural language processing. So I have a collaboration, and in our work, what we do is that students learning language, they write a lot of they have a lot of materials that they write, like for homework or tests and stuff, and we can use the writings that they use, the learner writings, to learn about. We can send it to a machine learning model and learn about their text. So we can learn, for example, how difficult their text is, or how correct their text is. And using this, we can find better ways to teach language. So it's really, yeah. And then now some more difficult topics. So yeah, so there's no way to avoid it. So one big problem with temporal neural networks is that, or any neural network, is that they require lots of data. But for time series, sometimes there's not a lot of data. Sometimes we have very small data sets. So because of that, we have to sometimes create data to build better, stronger models. And I have, we've done research in creating models, or creating, doing this thing called data augmentation and creating data intelligently. Like, for example, having a dynamic way of creating data, or using other dynamic programming methods to create data. And then another way to overcome small data sets is to use transfer learning. The general idea of transfer learning is that we can use a neural network trained on a lot of data to train the model well, and then fine tune it for small data sets. And this student, he's done a lot of different methods, including using out-of-domain data, or multiple data sets, or high-dimensional data. And I'm also interested in how to represent data. So not just how to train networks, but I also want to know, is what we give the neural network the best way, or the best kind of data, the most informative, right? So maybe just using the time series alone is not good enough. Maybe we can use other things like signal processing techniques to, we can give the network signal processing techniques plus the original data, and maybe we can create stronger networks. Or maybe, like in this work, I tried to overcome the temporal distortions by by having dynamic features. So features that change based on the input. And using this, we can learn stronger neural networks. And then on this topic, my student, he's tackling something called adversarial attacks. So in adversarial attacks, the idea is that it's possible to trick a neural network, right? So we can, if you give a neural network data that's modified by some small little noise, it's possible to break the data, to break the model. So what he wants to do is he's designing a neural network that has a defense against these attacks. So even if the input is attacked or corrupted by a bad person, then we can still have a correct output, a correct prediction. And then finally, so I have many works that cover this kind of topic, and it's basically how can we make neural networks that are robust to the problems of time series recognition, so the temporal distortions. So for example, in this work, I introduced something called a dynamic time warping neural network, and the general idea is that instead of is to take a MLP, so take a normal connection to an MLP, and then to directly dynamically warp the connections between the inputs and the weights. And in this way, now remember in the very beginning, I said that we have a problem of the inputs matching correctly. Well, in this method, this kind of dynamically forces the inputs to match correctly with where they belong. And in this way, we can have neural networks that can change and shift automatically depending on the input. Okay, so in summary, so time series are everywhere. We use them in daily life, and they're everywhere. And so it's really important to do time series recognition. But time series recognition is very difficult. We have many issues that many other types of data might not have. And it's also important because the lessons we learn from time series recognition connect to other fields like image recognition or statistical data recognition. And all these fields interact with each other, and we share different techniques and methods with each other, right? It affects other domains. And then my research in particular focuses on improving time series recognition. Okay, I think that's the end of my time. So thank you very much.
Thank you very much, Iwana Sensei, for your presentation. And it is very, very interesting to see like the difficulties, so that things that seem very similar at the beginning, that they can sometimes be very different. Please, if you have any questions to Professor Iwana, please do post them in the chat. But before there's any other questions, I wanted to ask a question myself. So at the very beginning of your presentation, you showed a graph where you basically say, we train any type of AI via, for example, we tell them it's a fish, or we tell them it's a TV or something like that, or we tell them it's a car. So the thing is very important, because one of the things is, I recently saw, maybe there's a famous documentary on Netflix right now. It's called The Social Dilemma, if you have heard of it. So it also interviews some of the people who are working on AI, and one of the things is the definition itself is extremely important, because any type of AI needs to know what is a fish. So, for example, in the green thing, you say, okay, that is a fish, but you need to first define it as a fish for the AI. You need to tell them that is what a fish is. If you could also say trick the AI and say this is a car. So they would, and you would just say that the fish is a car, and the AI would think, oh, that is what a car looks like from a human perspective. And then when you look at it, and you would look at an AI, and you would type, please show me a car, and it would always give you a fish. It's because the person who defined what is a car always typed it in as a fish. So basically, the thing is, and the problem, and I wanted to hear your opinion, is how important is it that the people who define and who train the AI also have the knowledge and the expertise and the responsibility and the ethical responsibility to input the data in a correct way, because otherwise we train AIs, and then AIs, if the people who train them either do not have the expertise or even have bad intentions, they can abuse it. For example, you can train an AI, what does a criminal look like? And in Social Dilemma, for example, they showed in the United States that if you train an AI with a certain image, a visual image of a criminal, then it will always think that that is a criminal from a visual point of view. So I wanted to hear your opinion on that. How important the first step is in terms of data and defining what it actually is that you input. For example, another thing would be, for example, environmental damage via satellite. You would train an AI to detect deforestation. You need to train it properly so that it can detect, so the person who inputs it and defines that this represents deforestation needs to have the proper expertise. Otherwise, an AI can give the wrong results at the end because it was not properly defined. So that is my question to you. How important is that step?
Okay, so actually, that's probably the most important step. So like you mentioned, oh wait, oh yeah, my mute's now. Okay, so like you mentioned, so the well, kind of the worth of the model is only as good as the ground truth, as the labels. So if the labels are bad, then the model is going to learn something bad, and it's not going to be able to learn very well. And actually, you could kind of see it empirically. So in this timeline down here, I mentioned that MLPs were invented a long time ago, 1960s or 1950s, but it wasn't until maybe around here that they're used. For a long time, people thought MLP or like natural neural networks were bad, but the reason why they're bad is because the data. Because back then we didn't have enough data. We only had the data sets they were using were too small or not well labeled enough. But nowadays, because the way computers advanced and we can now use GPUs and we can process data so much faster, now that's all that we're using is neural networks. And yeah, it's all because of the quality and the amount of data that we're able to access now. So so one unfortunate part about machine learning is that we have to trust the data and we have to trust the labels of the data, and because all the learning is done automatically by the computer. So if the data is bad, then the decision is gonna be bad. And we don't normally, except for some few models, we don't actually interfere with how the computer learns. Just so the data is so important.
Because what I always think about is like, if you would like raise a child in isolation and you would always show them a car and you say that is a fish, the child would grow up thinking that a car is a fish, and then it goes out into the real world and everyone says to a car, and the child is like, but that is a fish. So, and it's the same with the neural network. So I do think the labeling sometimes does not get enough, as you say, it's the most important, but I think sometimes the labeling is not given enough attention. And who does the labeling and what are the processes in terms of like, labeling in and of itself? Because in the end, we just usually see the end result, but we do not see what has been done at the initial stages of like, and an important factor is, for example, now with social media, for example, beauty standards, like, a lot of algorithms are trained to like kind of identify certain beauty standards. And then Instagram gives us like, what it thinks are common beauty standards. But that is just because of original labeling. And then an AI thinking, oh, that is what the current beauty standard represents. And then we're being fed with that. And I think that is very important in terms of the original labeling to say like, oh, that is just a beauty standard. It is not the beauty standard. So for example, and I think that is where labeling becomes very important. But apart from me, there's a lot of people who have questions. So let's go a little bit through the questions. So the first one is from Professor Sen, who is also at QAOS. I think the research on time series recognition is really important for the development of AGI. What do you think about its contribution to AGI?
Well, I think the biggest contribution is going to be language. So understanding language. So yeah, like I mentioned, language is also a time series in temporal data. And for something like AGI to exist, it has to understand language. And so that's probably going to be the biggest contribution.
Thank you very much. So next we have from one of our attendees, what is the best way to implement machine learning for smaller data sets?
The best way to implement it?
Yes,
actually,
so for example, if you do not have a lot of data,
yeah.
So how do you go about it?
Right. So actually, so many problems are not as difficult as you might think. So sometimes, so many of tons of the data sets I have are so tiny, like maybe like a handful, like 20 or 30 patterns, but they're still able to get like near perfect accuracy because the problem is not that difficult. So the first thing to do is just try with any data you have. And then if you can't get good accuracy with the data you have, then you look at things like right? Then you look at things like data augmentation and transfer learning. These are two super common methods of training your data set training your model when you don't have enough data. Yeah. So actually, transfer learning is especially common in image recognition, where you already automatically, or you first train the network with something called like ImageNet, and then you fine tune it for your own small problem. For time series recognition, it's a more budding field because time series recognition isn't as popular, but we're getting there into the same levels of image recognition. But anyway, yeah. So first I would start with transfer learning, and then if that doesn't work, then data augmentation.
Great. So next one would be the next question is in a time series like the analysis of the action, if two or more events occur at the same time in the time series of events, are there any recognition models to deal with this?
So kind of and kind of not. So okay. I'll save. Let's see, do I have a good picture of a time series? Yeah, well, maybe this one. So in the purest of pure time series, you can't have two things happen at the same time. Every time step only has one value. So in a normal time series, you couldn't. But this is only a one-dimensional time series. So you might have a time series that has I don't have a picture of one, but that might have many dimensions. So like, for example, no, I don't have a picture, just the person. So in one of the researchers in my lab, they're studying like they have wearable technology where like it has sensors, and in the glasses he might have like 10 different sensors, and each sensor is tracking another each sensor is making another time series. So if two things happen at the same time, a sensor will pick up, like one sensor will pick up something, and another sensor will pick up something else. And in this way, you can process a multi-dimensional time series. Yeah. So that's how you do it. So the answer is technically each time step only has one value, but also technically you can have multiple dimensions. So you can have multi-dimensional time series that can handle more than one event at one time.
Okay, I think that's a very concise, but yeah, no, it's a challenging answer. The next one is a much more concrete, scenario. So in a hospital scenario, there's a huge scale of tax data in electronic health records, and the person asking is concerned on identifying which patient undergoes adverse events through, for example, erroneous procedures, so medical mistakes or so, and how can we keep track of that? Through NLP, transformers, how do we make that happen? At present, it's usually through the voluntary reporting of stuff, but could there be ways of using AI or machine learning to basically detect mistakes in procedures through the electronic health records without necessarily the staff having to report it voluntarily.
Yeah. So there is. Oh man, I wish I had. So I don't have time to look through my computer, but so there's a whole field of this kind of research called anomaly detection, and maybe so. I'll first a small story. If you're at Kyushu University, there's these big green posts all over school, and maybe you never know what these green posts do, but actually the green posts are tracking people and counting people over time, and the purpose is that there was research done on wanting to know when crowds gather, why, like what kind of things happen. So like on a normal day, you might have students walking one direction, but maybe students might walk a different direction on a different day. So detecting these anomalies, so these problems, and seeing what caused the problem. It's a huge field of research done, in time series recognition. And probably the best way to do it is use any of the most state-of-the-art models, like a transformer or a CNN or something. But something interesting is the biggest problem is that getting the data. So one huge problem in machine learning is that we have to get the data, right? Like we talked about data, but medical data is especially difficult to get because it's sensitive, right? So it's like you can't have any names on it and you can't have any identification. So getting this data is very difficult. So if you could get the data, then yeah, it's easy to develop models for it, and there's lots of research done in that area.
Okay, with that, we just have a quick last question, and then unfortunately, we're running out of time, but we have one last question. So Danny Young asks, as pattern recognition technology develops so fast, how would a layman or laywoman keep up to make social judgments on the results decisions from AI generation? So the thing is, it goes a little bit into my first question. How would someone be able to detect, for example, how an AI was programmed and what the AI at the end produces is the result of let's say it unbiased or as unbiased as possible? Or where can you detect if you are confronted with results and people would tell you, oh, but that is not me, that is an AI that has produced that. So it must be like fair. So how would you go about as a layperson to detect that? Would you need to know about the original process?
I think this is a really difficult question, and I don't think it'd be possible. So as we progress in time, AI is getting better and better and better, and there'll be a point when it'd be impossible to detect whether if something was made by AI or decided by AI or not, or by a human. Even now, we're pretty close in a lot of things, like, right? So like if you saw these pictures, except for if you ignored the words, it would be difficult to tell if an illustrator drew this or if an AI drew this already. And yeah, so as technology gets further, it'll be more and more difficult. And unfortunately, you'll just have to trust the people who made it, because yeah, there's no way around it.
And then as a final question, which goes into that, do you think there should be a right of origin, sort of like with food products, where you are sort of entitled to know where has it come from? There needs to be like sort of an indication. So does AI generated product services or so, should they kind of carry like a digital watermark so that you could trace it back from where it comes from, so that even though I cannot get all the sources, I at least know to some extent where has this result been what has it been influenced by? So for example, what was the original data, or what were the original labels, things like that? Should there be a right to that, a right of knowledge, kind of?
I think if there was, it would have to be legislated, but that'd be impossible to monitor. So like big companies, they can have laws and stuff applied to them, and maybe they should do it anyway. But if I can do the same thing, but do it on my computer at home, who's going to know and who's going to stop me from doing bad stuff, right? So with how easy it is to access, and it's becoming even more easier and easier to access, it's going to be more and more difficult to prevent bad people from doing bad stuff. So I'm not sure if
but
yeah.
wouldn't that be an argument for everything? So why are we
yeah.
forbidding some drugs, even if there's always bad actors who do bad things anyway?
That's true.
So
Yeah,
I think we still try the best that we can, I guess.
That's true. Yeah, it's something that the big companies could do pretty easily. Like if you use, yeah, and maybe they should.
Yeah, I mean, it's like with illegal animal trade. You have like big actors and you have like small actors who do it in the very small level. That doesn't mean that we shouldn't prohibit it to some extent, I guess.
Yeah.
Well, anyway, with this really insight, and I think like, yeah, if there were a lot of questions, and I think this is a topic that really will gain even more pace in the future. But with that, I would urge you to also like reach out to Professor Iwana if you want to know more about his work, the work in his laboratory, the work in his research group, and just generally about AI, because I do think this is a topic that requires a lot of exploration, examination, and collaboration. So with that, I would say very much thank you to Professor Iwana for his really, really engaging presentation today. And again, please do reach out to him and his research group if you want to know more, if you want to see if there's any form of collaboration possible. And with that, we conclude today's 142nd edition of the Brown Bag Seminar. And with that, I would hand it over to the Curious Stuff to inform us of what is to come in the future. Thank you very much, and have a great day.
ブライアン先生、シューマハ先生、ありがとうございました。最後に事務局よりご案内をさせていただきます。まず、次回のブラウンバッグセミナーのご案内です。次回は来週6月5日水曜日午後12時10分より、九州大学病院 ARO 次世代医療センターの戸高浩二教授より、満たさない医療ニーズがなくなる日までと題し、講演を実施いたします。